I'm skipping through what I've written in the notes, and just as a bit of background, those explanatory notes, I usually just put up a slide and just bang on about it. So I tried to put what I bang on about down in words. So it mightn't be all that tidy. I am getting them edited, and Richard Eckhart, of some of these I've run past Richard Eckhart and he's added some comments to it. Some of them he hasn't had a chance to do yet. So I should say there will be an updated pack of this stuff coming out after Rich has had a look through them and made some comment. He's checked some of them, but not all of them, and that's what you'll see in the header comments at the top. I've got there not for circulation, confidential draft. It's really for your use. I'm just a bit mindful until we get them as a final copy that I don't want to see slabs of it repeated in people's newsletters and stuff like that until I've just checked off with Rich to make sure everything's kosher.
So Cam, we can work to distribute that next version later anyway.
Yes, yeah, happy to do that. And if people on the way through make a comment, oh, have you got a slide on such and such, or have you got more information on such and such, I probably have. I tried to limit the slides and I ended up with 100 odd.
Yes.
But I've literally got hundreds and hundreds of slides of different things. So if there's something particular you'd like a better example of, or a different example of, I can probably find it somewhere too for you to use.
All right.
All right, let's move on to. Happy to move on, Em?
Yep. Thanks, Cam.
Okay. This one, the metrics, I'm sure some people have already heard a fair bit of this stuff and carbon dioxide equivalents and so on, but it's a useful thing to explain because you can get tripped up quite often in workshops with people not having this full understanding. So simple way I go through it, I talk about, and I've already mentioned this, there are only some gases that capture heat and re-radiate them back. The main ones that we mentioned was carbon dioxide, methane, and nitrous oxide because they have more than 2 atoms in the molecule. And I've also mentioned that water vapor's in there as well. Because people say, oh, there's a heap of water vapor in the atmosphere. That's a greenhouse gas. Why are we bothering? So I'll put water vapor in there as well as that fourth one. So they're the 4, and it's because they have more than 2 atoms in the molecule. Something we need to get our heads around, and where there's been a lot of confusion and a few representative groups being a bit naughty at the moment and confusing things, is the way these different greenhouse gas molecules behave. One of them that we've got is methane, and methane is often referred to as a flow gas or a short-lived climate pollutant. It's the 2 different ways you'll hear it described. What that means is that when methane is created, it breaks down fairly rapidly in the atmosphere. It works on what's called an exponential decay curve, and the half-life, in other words, the time for 50% of that gas to break down, is roughly about 8 years. It varies a bit depending on who you Google and when you Google it. But in sort of laboratory type experiments, it's about 8 years for methane to break down. So it's called a flow gas in that you can create it, it disappears, you can create it again and it disappears on the way through over that 100-year permanency period we're talking about, or even the 25-year permanency period we talk about in Australia. The 2 other gases that we refer to, because we've knocked water vapor out, is carbon dioxide and nitrous oxide. They are what's called stock gases. And by stock gases, they have a half-life, and again, it depends on what you Google and read, but half-life well over 100 years. So the majority of carbon dioxide that's produced today will still be around in 100 years' time. The same with nitrous oxide. So the gases behave differently. So of the 3 gases, they don't all behave the same. 2 of them are what we call stock gases, that once you put them in the atmosphere, they stay there. Another one, you can create it and it disappears over time. And it's pretty important because those 3 gases, and because they behave differently, it makes it difficult for us to be able to compare them on a like-for-like basis particularly when governments and the international community are trying to develop policy. So they had a crack at trying to put them on the same comparative scale. And they did that, and they call it the global warming potential, or the relative warming potential over a 100-year period. So they said if that gas stayed in the atmosphere, knowing that they break down at different rates, if that stayed in the atmosphere for 100 years, then how much radiating force or how much heat would it capture and push back into the planet. And so we talk about the GWP 100, as it's commonly referred to, which is the global warming potential, 100 meaning 100 years of the time frame. There are GWP numbers for 25 years and 50 years and 20 years and so on, and they will have different numbers associated with them. And because I wanted to compare these different gases, ignore the four at the bottom there, the hydrofluorocarbons that we've got rid of most of off the planet now. We're not manufacturing those anymore. These are the three most important ones. When they compare the gases for those radiating forces, they give carbon dioxide a rating of 1, and then they compare the radiating forces of the other gases against carbon dioxide. And I often explain to people, it's a bit like a DSE rating. And I say, does everybody know what a DSE is? And they say, yes, I do. And it's a 50-kilogram animal that's maintaining condition, adult animal, and it needs 8.3 megajoules of energy. So I said if a cow weighed required 83 megajoules of energy, how many DSE would it be? It'd have a rating of 10 because it's 10 times 8.3. This is exactly the same type of process that's being used for the GWP values. So in other words, a methane which has a value currently at 28 means that you could put 1 methane molecule into the atmosphere or 28 carbon dioxide molecules into the atmosphere, and you would have the same warming potential. So the same amount of warming would occur with 28 carbon dioxides or only one methane. You could put 1 nitrous oxide into the atmosphere, or you could put 265 carbon dioxides into the atmosphere, and you'd have the same warming effect. So they've tried to compare those three gases over 100 years in relative terms to each other. Now, there's a lot of flaws associated with that because we know they break down over time, but this was the best they did in the early days. So when it first started in the late 80s, early 90s, they realised there were some flaws, but this at least gave policymakers some understanding of, should we be tackling nitrous oxide or should we be tackling carbon dioxide, because they have, stopping one of each of them has a different global warming effect. Okay. Now, and we've already sort of touched on this, how it's a moving line in the sand. In other words, the goalposts keep moving all the time. And here's a good example when I say to people that it moves all the time. As we learn more science around these gases and the way these gases behave, their relative global warming potential over 100 years to each other has changed. So AR just refers to what's called assessment reports, and I'll touch on this in a minute, but these are reports done by the international community that collates the last 5 to 10 years of research that's been done, and then they collectively get together and recommend to governments of any changes that need to be made in the assumptions of this greenhouse stuff going forward. So I've put 4 AR report periods in there. Carbon dioxide has got that standard, that's your 1 is your DSE rating. And you can see over time that from 2008, 9, 14, 15, which was the AR2 report, methane was considered 21 times worse than carbon dioxide. It then in another report went up to 25 times, and in another report went up to 28 times. And in the latest report that is now being adopted by countries around the world, methane, biogenic methane, so that's methane that comes from ruminant animals, and is part of a natural process, gets a global warming rating of 27. If it's been generated from fossil fuels, it gets a global warming potential of close to 30. And the reason why is that methane, when it breaks down to carbon dioxide. So for biogenic methane, because it is carbon that is already in the atmosphere that's going into the plant, that is then being chewed up by the animal, produces methane, we're not adding more carbon to it because that methane breaks down to carbon dioxide again. So we're not adding any more carbon dioxide, we're just circulating it round. Where from the fossil fuel industry, we are taking a carbon source which is underground, and we are bringing it up and putting it into the atmosphere. And as that methane breaks down, what's left is carbon dioxide, but that is new carbon dioxide to the atmosphere. So for the first time, it's been recognised that methane coming from livestock and those natural processes has less of a global warming potential than methane coming from the fossil fuel industry. Fossil fuel industry has argued for the last 20 years that methane is methane and we all should be considered the same. In this last report, it was recommended that the two get split up. So our methane is a little bit less than where it was before. So that means if you're in livestock, the methane number has changed 4 times in the last 12 years, which makes it difficult when you're doing a calculation to want to claim anything. My emissions are X or Y, because the numbers will change. Currently, the Australian government's still using 28, either in the next month or 2 or early next year. That will change to 27 for biogenic and 29.8 for fossil fuels. But at the moment, you'll see the calculators are still working with methane at 265 and nitrous oxide, methane at 28 and nitrous oxide at 265. That will change relatively soon. Okay, so that's just an overview of those different gases. Now, GWP 100 in particular for methane has some real challenges to represent that accurately. And this is where a lot of noise has happened over the last few years. It's the best we've got though, and that's why the international community, while recognising that this is not perfect accounting, it's probably the best we've got and it's good enough to go forward on. So GWP 100 is accepted globally as the way to go about it, except for a few people that want to poke the possum. And it's because they run this sort of an argument. So I'm just going to give it to you because there will no doubt be people in your workshops that you do, if they've got livestock, that will raise this with you. And so you just need to understand the behaviour of methane, how it breaks down, and how some of the claims that are being made at the moment just aren't true, and this is the way to unpick them. So if we consider 100 molecules of methane that's released into the atmosphere, and it's got a half-life of 8 years. So that means, in other words, after 8 years, 50 of those 100 molecules will have disappeared. You could draw that as a graph, and that's a simple decay curve graph that I've drawn there. So if you think you've got 100 methane molecules there, in 8 years, it's dropped down to 50. And of those 50 molecules, in another 8 years, 25 of those have disappeared. So you've got 25 left after 16 years. Of those 25 molecules that are left, half of them disappear in another 8 years. So then you've got 12 and a half molecules left, and so on. So it decays along that with a half-life of 8 years. I often do that instead of using a graph. I can often do that on the whiteboard, and I just get people to join in and say, okay, let's say at year 0, you've got 100, at year 8, you've got 50, at year 16, you've got 25, and so on. So it gives people a chance to actually do the sums in their head so they understand how this breaks down over time. Now, what GWP 100 is trying to do is flatten that out so it's a standard number across 100 years. And that's where the 28 comes from. So the 28 would go across about there, and that's trying to represent that curve as a flat line. Now, it's not as simple as just flattening that out, because there are other reactions that occur as methane ends up being carbon dioxide. It reacts with hydroxy ions, it reacts with ozone and a whole lot of other things on the way through. So it's not a simple calculation, just squashing that graph and getting the straight line, but that's what they've tried to do. So important to recognise they've tried to take a curve like that and turn it into a straight line, which means in the early days when methane's being produced, the calculation, the GWP 100 calculation, is grossly underestimating the methane and the warming effect from there, but then grossly overestimating it in the latter years. But it's this graph that some advocates are saying we're doing methane all wrong and the calculations aren't credible. One thing that they claim, and you may have heard of, is that methane's gone in 12 years. I can't see people in the audience, but I'm hoping someone has heard that before. But there's this claim that I don't know why we bother about methane because it's disappeared after 12 years. clearly looking at that graph, that is not the case. What is actually being argued is that the average time methane stays in the atmosphere is 12 years. Unfortunately, the word average disappears and most people don't quite understand what average means. So they just think that methane is gone in 12 years. You can clearly see on this graph that after 12 years, we still have about 35 molecules of methane left that were produced 12 years earlier. So methane has not disappeared. Okay, there is still some there. But if you average that out over 100 years, because you're counting lots of very low numbers down here, the average comes down to 12 years. Hopefully I haven't confused people with that, but it's a really important point to get across. Cattle Australia, so the so-called peak body for the beef industry, are running around putting out press releases saying methane disappears after 12 years. I've dropped the word average out of that statement when it should be an average of 12 years. More to the point, though, is that when methane exists in the atmosphere as a methane molecule, it has a warming effect 128 times carbon dioxide. Okay, so methane, when I said it was 28 over 100 years, in fact, methane, when it's floating around as a molecule of methane, is 128 times worse than carbon dioxide. Okay? But as it breaks down and you've got less of it and it turns into carbon dioxide, we have a lesser amount that's at 128 and we have an increasing amount that's at 1 because it's turning into carbon dioxide. So even down here at 30 years, we still have some methane here, and every molecule, even though there isn't much of it left, is 128 times worse than carbon dioxide, even though it's a small amount. Okay, the 28 over 100-year period is tried to take into account that change. But that idea is lost, and everybody is just saying methane is gone in 12 years, which is clearly not true. But it's gained a lot of traction. You see reported time and time again in the newspapers. You see press releases from agricultural lobby groups saying it, and it is just wrong. Okay, it is just wrong. One of the arguments, though, that the industry also uses it because it's got, a graph that looks like that. If you repeated and did this year after year after year, you would get a graph that looks like that. So just to explain, that graph that I've got there is the first bit of that graph there over that period of time. Then if you add the next year, another one of those on top, and then another one on those on top, and another one on those on top, after a period of time, at around about 50 to 60 years, the amount of methane that you're putting into the atmosphere in that year is offset by the degradation of the 59 previous years of methane. So each year it's degrading and degrading at a different rate. All of those 59 other years where it's degrading is equivalent to what is being produced by that methane in that year of it being put out. So the second argument that some of these lobby groups and industry groups run with is that methane in a stable situation is not adding anything more to the climate. In other words, our methane in the atmosphere is balanced from a livestock point of view, and therefore we are having no warming effect on the climate. So they talk about it being climate neutral as far as that goes. If you've got a stable herd or flock that is producing that same profile every year, theoretically for 60 years. Okay. There are a couple of omissions in that logic. The first one is, while that operates right for 60 years, as long as there's methane in the atmosphere, it's warming at 128 times. So we end up with this legacy heat load being produced by even methane that's 30 or 40 years old. The little bit that's left is still pumping a hell of a lot of heat into the oceans. And that's where it's being stored. And it's being stored a lot longer than the actual lifespan of the gas that created that heat. And so if we just count gases, we miss the point. The point is, when it's in the atmosphere and remains in the atmosphere, even at a decreasing rate, it is still pumping heat into the oceans, and the heat in the oceans will dissipate much slower than the dissipation or the breakdown of that methane in the atmosphere. Okay. So it's a really important point to get your head around. Hopefully the notes will explain that if you've missed some of the stuff that I've spoken about there, but inevitably you will get people saying that methane only lasts for 12 years. Why are we bothering with it? Okay. We need to be able to get down to a level of being able to explain what's happening here and, in a sense, debunking this. While we're not adding any more methane to the atmosphere, we still have a lot of methane in the atmosphere. And while that exists there, it is putting heat into the oceans and therefore creating the climate change problems that we're having to deal with. All right, so as an alternative to that, a number of industries have been talking about using a different metric. Instead of GWP 100, they're talking about using a thing called GWP star. So GWP star tries to take into account, or claims to take into account, the degrading effect of methane because it breaks down so quickly. And the equation that they use as an alternative to GWP 100 is this one, that the carbon dioxide equivalent that is produced is 128 times the amount of methane that you produce from your herd or flock today, minus 120 times the methane that your herd or flock produced 20 years ago. Okay, so that's what the equation has distilled down to. So instead of saying the methane that was produced, let's say if we use GWP 100, we produced 100 tonnes of methane, you'd multiply it by 28, which means you'd have 2,800 carbon dioxide equivalents. The calculation would be very different. It's 128 because that's the warming potential of methane today, minus 120 times over 20 years. So that's the equation that they're using. If you run some sums on this, and this is a bit busy, but I'll just step you through it, you can understand how they prosecute the argument in some examples, but then avoid it in others. So if you take a stable herd or flock, so let's say you're a farmer and you've got the same amount of animals today as you had 20 years ago. So let's pretend today that you produced 100 tonnes of methane today, and 20 years ago you produced 100 tonnes of methane because you've got exactly the same numbers of animals. Okay. Today, if you use GWP 100 as a calculation, it's 100 times 28, so you get 2,800 CO2 equivalents, tonnes of CO2 equivalent being produced. If you use GWP star, it's 128 times 100 minus 120 times 100, which means you'd be left with 800. So if you've got a stable herd or flock, they're saying you shouldn't be pinged 2,800 as the warming potential, or the carbon that you need to, carbon equivalents you need to soak up. You should only be pinged 800. So you get a smaller warming value if you use GWP star if you have a stable herd or flock. If your herd or flock declines, so let's say 20 years ago you had 100, but now we've only got 70 because you've gone into more cropping, let's say, and less livestock. In simple terms, that GWP 100 calculation's gone from 1960 to actually minus 3,040. So 128 times 70 minus 120 times 100 would give you minus 3,040. And so they argue that the livestock industry, if the flock or herd is reducing, that you have a relative cooling effect on the climate. Still producing methane, still producing 70 tonnes of methane, but the equation would suggest that you're actually cooling the planet by having those animals still on the place, which again is a bit of nonsense. The one that they don't talk about is if you increase your flock or herd. So if 20 years ago you had 100 and now you up it to 130 by running some more livestock, let's say you're more productive, you're running more DSEs per hectare, the GWP star actually makes you worse off than GWP 100. And if you take it even one step further and say, okay, I had no livestock, because let's say I was all cropping, and now I've produced this much methane from my livestock, and while there'll be a negative from not having your crop emissions, you can see the massive difference by increasing those herd numbers. And so you have a massive warming value. Now, the proponents of GWP star only talk about the first two. This is the reality for the other two. okay? And when we've done our numbers at home, we've increased our emissions over the last 20 years. We are actually worse off using GWP star than we are using GWP 100. So a couple of things that are issues from this. First of all, I do not know any farmer that has their methane calculation from 20 years ago. So how the hell are you ever going to use this as a calculation? And the second one is that there's an equity issue with developing countries. When the IPCC first came together, one of the things that was agreed to as we move towards a lower carbon economy around the world is that developing countries will not be adversely impacted compared to developed countries. And so the argument here is that you could have 100 stable herd of 100 and you would be treated better than, let's say, if you were a farmer in Kenya that went from having one animal 20 years ago to 2 animals today, your GWP measurement would be higher than someone that's got a stable or declining flock, even though you're producing a hell of a lot more methane. So there's this huge equity issue. So while groups like Cattle Australia and a number of others will advocate for GWP star being used, it only really stacks up in developed countries. Third world countries are against it, and the IPCC are against it. So we will end up with using GWP 100 despite the flaws in it. Okay, so going forward, we will not be using GWP star, or I can't see we'd be using GWP star, even though at the moment there's a hell of a lot of noise around it by some rather influential lobby groups. Okay, and just to finish that off, if I come back to this diagram, which I quite often use, you can remember I said it, the animals comes into a form of stage 4 before it breaks down to carbon dioxide. And if you think of it, it's the form of carbon, it's methane, and it's 128 times worse when it comes out. And it's also got that legacy heat load that it pushes into the ocean before it breaks down to carbon dioxide as part of it. Okay. And so the length of time it declines, it's 60 years, not 12 years as people talk about. And the last one, which I'll just chuck in, is that at the moment we use a half-life for methane of 8 years. As we increase the amount of methane that's in the atmosphere, methane breaks down by a reaction with what's called hydroxy ions that are created by infrared light and ultraviolet light in the upper part of the atmosphere, and that's being formed at a fixed rate. So the stuff that methane reacts with has got a fixed supply each year based on what the sun produces or in the atmosphere that it produces. As we increase the amount of methane, but we don't increase the amount of hydroxy ions that are there to react with it, then the time for that methane to disappear is going to increase. So that, in other words, the half-life will increase because we're increasing the methane, but we're not increasing the other gas that reacts with it. And so they talk about, it's called the perturbation time, but basically the half-life of methane, some of them are claiming the perturbation time now is up to 12 years because of the extra methane that we've put in the atmosphere. So instead of taking 8 years for 50% of it to break down, they're talking it can be up to 12 years for 50% of it to break down. So it just means that as we add more methane to the atmosphere, that the time it's going to take to break down is going to get worse, which means the heat load effect in the oceans is going to get greater.